Ice and fire are traditionally viewed as opposites. Ice halts motion and preserves organic matter. Fire consumes and destroys. One represents stillness, the other represents a violent release of energy. But thousands of meters down, beneath the crushing weight of the ocean, that distinction disappears. Scientists discovered seafloor fractures glowing with blue crystalline light. When researchers pulled samples of white material from the mud, they appeared to be ordinary ice. But when touched by a flame, the solid erupted into blue fire. It hissed and burned while remaining partly solid. This is methane hydrate. Its existence is a product of molecular geometry and pressure conditions that operate entirely outside our daily experience. Instead of a simple solid, deep-sea pressure and near-freezing temperatures force water molecules into clathrates, microscopic architectural cages trapping methane inside. This massive compression ratio means 1 cubic meter of hydrate contains over 160 cubic meters of gas. Because methane is a potent hydrocarbon fuel, the scale of this reserve is difficult to overstate. Estimates suggest methane hydrates contain more carbon than all known coal reserves combined. That volume also exceeds all known global oil and conventional natural gas reserves. This discovery has alerted energy-starved nations. Japan, China, and India are currently investing in extraction research, viewing these hydrates as a primary energy source for the coming centuries. By looking into the deep ocean, humanity has located what may be the largest untapped fuel reserve on the planet. This energy is the product of millions of years of biological decay. Plankton and ancient marine life sink as marine snow, accumulating in deep sediments. Deep underground, microbes break this organic matter down in an environment without oxygen. A primary byproduct of this chemical process is methane gas. Usually, gas rises and escapes, but the extreme cold and crushing weight of the deep ocean prevent this, forcing the gas into water cages to form vast geological layers of hydrate. Over eons, Earth has transformed the ocean floor into a silent, high-pressure carbon vault. The stability of this vault depends entirely on the environment remaining cold. If the narrow pressure-temperature balance is broken, the solid material dissociates and the gas expands. Warming ocean temperatures now threaten these deposits. As heat penetrates the seafloor, hydrate layers across the continental margins begin to destabilize. This is a critical climate risk because methane is a potent greenhouse gas. Over short timescales, it traps significantly more heat in the atmosphere than carbon dioxide. Warming water dissolves the frozen cages. Methane streams rise and enter the atmosphere. Once there, methane amplifies the greenhouse effect, trapping more solar heat. This trapped heat further warms the oceans, destabilizing even more hydrates. This self-amplifying cycle creates a feedback loop, leading to a rapid, uncontrollable increase in global temperatures. The geological record suggests this has happened before. 56 million years ago, during the Paleocene-Eocene Thermal Maximum, the planet experienced one of its most rapid warming events. Scientists identified a sharp negative carbon isotope excursion from this period. This chemical signature is consistent with a massive release of biological methane from the ocean floor. Hydrates also present a physical hazard. These frozen layers help stabilize continental slopes. When they melt, the surrounding sediment weakens, which can cause the seabed to collapse. This likely occurred 8,000 years ago during the Storegga slide. A massive underwater landslide near Norway displaced thousands of cubic kilometers of sediment, generating tsunamis that devastated North Atlantic coastlines. This instability is now visible in the Arctic. As permafrost melts, shallow hydrate deposits are destabilizing, causing the ground above to cave in and erode. The planet bears the scars of these past events, providing a physical archive of what happens when these deposits awaken. Despite these risks, nations are moving to extract this resource. We are deploying massive offshore drilling vessels to tap the same material that has historically triggered these collapses. Safe extraction is an engineering challenge because the material is physically unstable. Pulling hydrates toward the surface causes them to decompose rapidly, turning the solid ice into a violently expanding gas. Global superpowers are now conducting active extraction tests. By lowering the pressure in the subsea deposits, they are attempting to melt the hydrates intentionally and capture the methane before it can escape. This puts humanity in a difficult position. We must find a way to extract this transitional fuel without triggering the very feedback loops and geological collapses we see in the ancient record. In the crushing darkness of the deep sea, mountains of invisible fire remain locked in their crystal cages. These colossal reserves are waiting. The rising temperature of our planet will ultimately determine whether they remain frozen or begin their next violent release.